Falling objects. Newton's second law meets gravity and drag. Newton's second law tells us that the motion of an object depends on all the forces acting on it. In this experiment, we will look at two of these forces, gravity and drag. We will drop an object and gather data about how it falls, using a program called Tracker. We will transfer our data to a program in VPython, which will analyze our data to create two computer models based on Newton's second law. Our first computer model will show us how the object would fall if gravity is the only force acting on it. This would be the case if you dropped it in a vacuum. Our second computer model will add in the effect of the drag caused by air resistance. Finally, we will combine all of our data in a spreadsheet and generate a graph comparing our experimental result to the model with gravity only and the model with gravity and drag. Here's how we did our experiment. We used the following things. We have a balloon weighing 1 gram. We have a teaspoon of water weighing 4.7 grams to help the balloon fall straight. And we used a high staircase from which to drop the balloon. That went pretty fast, didn't it? Let's take a look at how it shows up in Tracker. Okay, you can see that as it fell, the distance it fell between each frame was larger and larger because it was falling faster, but the curve tells us that at one point it reached terminal velocity and stopped going faster. Now it's time to move our data to a special version of Python that will generate a computer model of how our object would fall if it were affected only by gravity, and then how it might fall with both the force of gravity and the force of air resistance, or drag, acting with gravity. We will have to estimate the possible coefficient of drag to do this. Here's how we set up our model. First, we set up the system properties and initial conditions. We put in the mass of our balloon in kilograms. It was 5.7 grams, or 57 thousandth of a kilogram. We put in the starting point, the vector values for that. We wanted it to start at the origin. The time increment we put in was 1/1000th of a second. We could easily have gotten away with 1/100th of a second. This generated way more data than we really needed to have. We put in the gravity at the Earth's surface, which we know to be 9.8 newtons per kilogram, approximately. We also put in the y-axis unit vector, which would be 0 and 0 for the x and the z. And we put in a guess at our magnitude of the drag force because we wanted to include that in our final model. Oh, there we go. This is how we set up our calculation loop in our Python program. By the way, this is VPython, otherwise known as Visual or Virtual Python. First of all, we tell it how long we want it to run. Then we show the force of gravity in the system, which we enter, the force of drag in our system. Actually, those things were already there in the template we were given. Then we put in Newton's second law of motion expressed in Python. And we tell it to update the position of the ball each time it goes through the loop, and finally to advance the clock. And this is what our program looks like when it runs. And this is what our program looks like when it runs. It makes a graph. You see on the left is the most interesting part because you can see the weight or gravity force is shown in the greenish yellow arrow, and the blue arrow is the drag force. The red is our balloon or ball that we used. You'll notice that it did reach its terminal velocity fairly early in the graph right around in this area here, it starts to get to the point where you could draw a straight line on up. So terminal velocity, it doesn't increase much in velocity here. It's pretty steady. So along somewhere between 3 and 4, a little over 4, it was at terminal. Summary and what if. Here is a graph generated by a Google spreadsheet. Our experiment is in pink. The blue line is the model with gravity only, and the green line is the model with both gravity and drag. From this we can see that the motion caused by gravity and drag was close to that predicted by Newton's second law. It appears that we underestimated the effect of drag on our model. That is what caused the model to differ from our experiment. What if we threw the object down instead of merely dropping it? I believe this would cause it to move faster in the beginning and reach its terminal velocity even sooner than it did.